Hello everyone. Today we will discuss one of the basic rules in calculus which is used for the evaluation of limits. Suppose we want to evaluate a limit of the kind limit x tends to a f of x divided by phi of x. Okay, usually using the basic rules of limits, this is actually equal to limit x tends to a f of x divided by limit x tends to a phi of x. And suppose the functions f and phi, they are continuous, then this is equal to f of a by phi of a. Okay, and in some cases there may be a chance that both the functions f and phi, they take the value 0 at the point a, so that this will become 0 by 0. That means f of a equal to 0 and phi of a is also 0. So in such a case, the limit of x tends to a f of x by phi of x equal to 0 by 0, which is a meaningless quantity. Okay, in such cases, we can use some other rule which is called the L'Hopital rule for evaluating the limits. Okay, a quantity of this kind is called an indeterminate form. There are many other indeterminate forms of the type infinity by infinity, and infinity minus infinity, 0 into infinity, 1 raised to 0, 1 raised to infinity, infinity raised to 0, etc. Okay. In all these cases, we can use the L'Hopital rule for evaluation of the limits of this kind. Okay. Now we will see how to evaluate the limit as x tends to a f of x by phi of x using the L'Hopital rule. Okay. Suppose this limit reduces to the form 0 by 0 when we evaluate using the usual rules of limits. Okay. Suppose the functions f and phi, they are differentiable and the derivatives of orders up to n, x is for both phi and f. Okay. In that case, the limit x tends to a f of x by phi of x will be equal to the first quantity among the expressions limit x tends to a f dash x by phi dash x, limit x tends to a f double dash x by phi double dash x, etc. Limit x tends to a fn x by phi n x. Okay. And of course, these quantities, this limit is actually equal to the first among these quantities, which is not of the form 0 by 0, provided that limit exists. In order that this quantity equal to one of these expressions, it should not be of the form 0 by 0, and that limit should exist. Okay. Now we will see a formal proof for this particular statement, statement of L'Hopital rule. Okay. Suppose we put x equal to a plus h, then as h tends to 0, we can see that x tends to a. Okay, x equal to a plus h, so that h tends to 0 will imply x tends to a. Okay, so we have limit x tends to a f of x by phi of x equal to limit h tends to 0 f of a plus h by phi of a plus h. Okay. Now we can expand these quantities f of a plus h and phi of a plus h, because we are assuming that f and phi are differentiable functions. We can expand these quantities using the Taylor's theorem. Okay. So this is equal to limit h tends to 0 f of a plus h into f dash of a plus theta h divided by phi of a plus h into phi dash of a plus theta 1 h, where these quantities theta and theta 1, they are such that 0 less than theta less than 1 and 0 less than theta 1 less than 1. Okay. Now, here the value of f of a and value of phi of a both are actually 0. Okay, that is why we are using this particular result or the rule. Okay, since f of a and phi of a are 0, this quantity, this will be actually equal to limit h tends to 0 f dash of, h into f dash of a plus theta h by h into phi dash of a plus theta 1 h. Okay. Now this h, this quantity can be cancelled, so that you will be getting limit as h tends to 0 f dash of a plus theta h by phi dash of a plus theta 1 h. Suppose this limit exists. So this as h tends to 0, this is equal to f dash a by phi dash a. Okay. So the quantity limit as x tends to a, f of x by phi of x, that is equal to f dash a by phi dash a. Actually this f dash a by phi dash a is equal to limit as x tends to a, f of f dash x by phi dash x. Okay. So this, if this quantity exists, then we can see that limit x tends to a, f of x by phi of x. Suppose this quantity is again of the form 0 by 0. We can again apply the same argument, so that this quantity will be having a Taylor series expansion of this kind using a limit of this kind, so that if this quantity f dash a by phi dash a is again 0 by 0, we can again repeat the same argument. Okay, and as before, we can evaluate the values limit x tends to a, f dash x by phi dash x, and so on. Okay, so that the value of limit x tends to a, f of x by phi dash x, f of x by phi of x can be evaluated by finding the limits of the derivatives of the functions. Okay, that is the L'Hopital rule. Now we will see an example where this L'Hopital rule can be used to evaluate limits. Okay, we will start with one of our famous result, which is limit x tends to 0 sin x by x, that is equal to 1. Okay, suppose we try to evaluate this limit using the usual method, then this limit will be actually equal to limit x tends to 0 sin x divided by limit x tends to 0 x. Okay, in that case you will be ending up with a value 0 by 0, which is not acceptable. Okay, so to evaluate this limit, you can apply the L'Hopital rule. Okay, suppose this quantity is written as this limit x tends to 0 sin x by x, that is equal to, using the L'Hopital rule, we have to evaluate the derivatives of numerator and denominator to evaluate this limit. Okay, so this is equal to limit x tends to 0, the derivative of sin x, which is cos x, and the derivative of x, which is 1. Okay, so this is equal to limit as x tends to 0 cos x. Okay, now we know that cos x is a continuous function, so that this value will be equal to cos of 0, which is equal to 1. Okay, so using this L'Hopital rule, it is very easy to prove that limit x is 0 sin x by x is equal to 1. Okay, usually we use some other methods or geometrical methods to prove this limit. By using this L'Hopital rule, it is easy to show that this result is equal to, this limit is actually equal to 1. Okay, now we will see another example, that is limit x tends to 1 minus x by log x. Okay, limit x tends to 1 minus x by log x. Again, if we use the usual methods, you will be getting 0 in the numerator and again 0 in the denominator, because log 1 is equal to 0. Okay, so in this case also it is possible to use the L'Hopital rule for evaluating this limit. So using the rule, this is equal to limit as x tends to 1, derivative of the numerator, which is 0 minus 1, divided by derivative of the denominator, which is 1 by x. So this is equal to limit as x tends to 1 minus 1 by 1 by x, which is equal to minus 1. Again, this limit can be evaluated using the L'Hopital rule, even if this reduces to the form 0 by 0. Now we shall see another example where the given limit reduces to the form infinity by infinity using the usual methods. Okay. Limit as x tends to 0 log x divided by cot x. Okay. Again, if we evaluate the limit using the usual method, then this will be log 0. Log 0 is equal to minus infinity, and cot 0. Cot 0 is equal to infinity. So it reduces to the form infinity by infinity. Okay. So this reduces to the form infinity by infinity, which is again an indeterminate quantity. Okay. So again, we can apply the L'Hopital rule for evaluating this limit. This limit will be equal to limit as x tends to 0, derivative of log x, which is 1 by x, and derivative of cos x, that is equal to minus cosec squared x. Okay. So you will be having this or we will just make a rearrangement so that you will be having this limit is equal to limit as x tends to 0 minus sin squared x by x. This cosec squared x we brought into the numerator, that is minus sin squared x, and this x in the numerator, that is brought to the denominator. Okay. So again, when we try to evaluate this limit using the usual methods, this will be sin 0 by 0, which is a 0 by 0 form. Okay. So again, we ended up with an indeterminate quantity, so that again we can apply the L'Hopital rule. So this is equal to limit as x tends to 0, derivative of sin squared x minus 2 sin x cos x divided by derivative of the denominator, which is 1. Okay. So when we evaluate the limit, the numerator in the numerator the value will be minus 2 sin 0 cos 0, and sin 0 we know that it is equal to 0, so that this will be numerator will be 0 and denominator will be 1, so that this limit is equal to 0. Okay. Now we shall see how to evaluate the limits when we are given a limit of the form limit x tends to a, f of x raised to phi of x, and it reduces to a form that it will be of the form 0 raised to 0 or infinity raised to 0, etc., which reduces when we apply the usual method. Okay, we shall see an example. Suppose we want to find the limit as x tends to 0, sin x raised to tan x. Okay, so if we evaluate this limit directly, you will be having sin 0 raised to tan 0. Sin 0 is 0, and we know that this tan 0, that is again 0. So it will be of the form 0 by 0. So this is a 0 raised to 0. So this is a limit which reduces to the form 0 raised to 0. So in this case, we will take some k equal to limit as x tends to 0 sin x raised to tan x, so that the log k you will be having limit as x tends to 0 tan x into log sin x. Okay, here the log function can be taken inside the limit because this log function is a continuous function, and so you will be having log k equal to limit as x tends to 0 tan x log sin x. Okay, now this quantity we can write it as this is equal to limit as x tends to 0 log sin x by cot x. Okay, so when we evaluate this this limit using the usual method, you will be ending up with the log sin 0 divided by cot 0. The sin 0 is equal to 0, and cot 0 you can see that it is equal to infinity. So again, this limit will not exist if we evaluate using the usual methods. So we will try the L'Hopital rule, so that this will be equal to, this quantity will be equal to limit as x tends to 0, the derivative of the numerator, that is 1 by sin x into cos x, divided by the derivative of the denominator, which is minus cosec squared x. So this is equal to limit as x tends to 0, cot x divided by minus cosec squared x. Okay, so this will be equal to limit as x tends to 0, this cosec squared that we will bring into the numerator, so that this is minus sin squared x divided by this cot x that we will be bringing into the denominator, so it will become tan x. Okay, so this is equal to again limit as x tends to 0. Again we will have to apply the L'Hopital rule because it is of the form 0 by 0 when we try to evaluate using the usual methods. So this is limit x tends to 0 minus 2 sin x cos x divided by sec squared x. Okay, so this will be equal to, when we make x tend to 0 in the numerator, you will be having 0 because sin 0 is equal to 0, and in the denominator sec 0 is equal to 1, so that you will be having 0 as the answer. Okay, and this is the value of log k. Actually we need to find the value of k. So the value of k will be equal to e raised to 0, e raised to the value of this limit, that is equal to 1. Okay, so the initial limit will be equal to 1, that is limit x tends to 0, sin x raised to tan x, that value will be equal to 1. We shall see one more example where we can use the L'Hopital rule. Suppose we want to find limit x tends to 0, cot x raised to sin 2x. Okay, here if we evaluate the limit using the usual method, you will be ending up with a form infinity raised to 0, which is again an indeterminate quantity. Okay, so again we shall take k equal to limit as x tends to 0, cot x raised to sin 2x, so that log k equal to limit as x tends to 0, sin 2x into log cot x. Okay, so this is equal to, we will just rewrite this limit as limit x tends to 0, log cot x divided by cosec 2x. Okay, so log k is equal to this limit. And now if you try to evaluate this limit, this log cot x, you will be having log infinity, which is infinity, and cosec 2x you will be having as x tends to 0, that will be again infinity. Okay, so again it is of the form infinity by infinity, so that we can apply the L'Hopital rule to evaluate this one. So this is equal to limit as x tends to 0. When we find the derivatives, the derivative of the numerator will be 1 by cot x into minus cosec squared x divided by 2 cosec 2x cot 2x. Okay, so the numerator will again reduce to limit as x tends to 0. The numerator we can simplify the numerator, so that you will be having minus 2 cosec 2x divided by, in the denominator also, actually there is a minus sign here, that minus 2 cosec 2x cot 2x. Okay, so this is equal to limit as x tends to 0. When we cancel the minus 2 cosec 2x in numerator and denominator, you will be ending up with 1 by cot 2x, which is equal to limit as x tends to 0 tan 2x. So you will be having the value as tan 2 into 0, which is 0. Okay, So the limit as x tends to 0, cot x raised to sin 2x, you will be getting the value 0. Okay. Sorry, that is the value of actually log k. Log k is equal to 0, and again the required limit k, that is equal to e raised to 0, which is again 1. Okay. So the limit as x tends to 0, cot x raised to sin 2x, you will be having the value 1. Okay. So using this L'Hopital rule, it is easy to find limits of this type, or when we find a limit which reduces to an indeterminate form, and it can be easily evaluated using the L'Hopital rule, especially when we have a mixture of functions. There are functions from log functions, exponential functions, sine functions, rational, other rational functions, or polynomial functions, etc. In that case, we can use the L'Hopital rule effectively. Okay, that's for today. Thank you.